Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Dip Pen Nanolithography from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, dip pen nanolithography technique is discussed. Also, the various materials which are used for the deposition are studied and the advantages are discussed in this module. In addition, the applications of dip pen nanolithography are discussed along with its properties and advantages. Finally, thermal dip pen lithography is also studied in this module. Now, what is dip pen nanolithography? Dip pen nanolithography, abbreviated as DPN, is a type of scanning probe lithography method wherein the tip of an atomic force microscope or AFM draws desired patterns onto a substrate directly. This technique can be used on various types of substrates and different types of inks can be used to draw the features. The most common use of this process is in imprinting alkane thiolates on a gold substrate. Patterns of up to 100 nanometer can be drawn using this technique. Dip pen nanolithography is nanoscaled analogous to dip pen. In DPN, tip of AFM cantilever works as pen which is coated with the compound which needs to be deposited as ink. This tip is positioned over the substrate or paper to write the pattern. Nanomaterials can be directly deposited over the substrate of choice by using this technique. This technique has also been scaled for simultaneous patterning using two-dimensional arrays of 55,000 chips. This technique has been used in chemistry, material science, life science, etc. The applications are as ultra-high density biological nanoarrays, repairing additive photomask, etc. Beginning with the development of dip pen nanolithography, Josh and Burt first reported the uncontrolled transfer of the molecular ink from AFM tip in 1990. They had concluded that it was not possible to create stable nanostructures by transferring alkane thiols on a gold substrate. Chad Merkin, while working at Northwestern University, investigated this process independently. He concluded that under specific conditions, chemically adsorbed stable monolayers could be created on a substrate by transferring the molecules in a controlled manner. They described the process as a high resolution lithography and termed it as DPN, that is, dip pen nanolithography. Merkin and co-workers got this process patented. Since then, the technique has been expanded to include liquid inks as well. Noticeably, the deposition mechanisms which are involved in liquid inks are different from those for molecular rings. Figure 1 shows typical DPN technique. Here ink contains the nanomaterial which diffuses from the tip via a water meniscus. Let us now discuss about the deposition materials. Coming on to molecular inks. Molecular inks essentially comprise small molecules which are coated on the DPN tip. These molecules are transferred to the surface of substrate via a water meniscus. The tip can be coated by two means. Either the required molecules can be vapor deposited on it, or the tip can be dipped, that is, dip coating in a solution of the molecular ink. When dip coating is used for coating the tip, the solvent must be removed before beginning the deposition process. The rate of deposition of a molecular ink is controlled by the diffusion rate of the molecules, and it is molecule specific. That is implies that it is different for different molecules. The pattern size is determined by the dwell time of the tip or surface, and it may vary from few milliseconds to a few seconds. Another factor controlling the size of the pattern is the size of water meniscus, which in turn is influenced by humidity. When the radius of the curvature of tip is much smaller than the meniscus. The characteristics of these inks are: the process is driven by water meniscus, although exceptions can be there. Then the resolution is of the order of 50 to 2000 nanometers. Also, there is no multiplex deposition. In addition, the molecular inks might be specific to the substrate. Typical examples include alkane thiols, which are patterned over gold substrates, and patterning silanes, that is, solid pastes over glass and silicon substrates. Another type of the deposition material for DPN is the liquid ink. Any material which is liquid under deposition conditions can be deposited as liquid inks. The deposition mechanisms depends upon the interaction between ink and tip, liquid, which is the ink, and the substrate, and viscosity of the liquid. Owing to these interactions, the minimum size of the pattern is limited to approximately 1 micron. This depends upon the contact angle of liquid. High viscosity of liquid provides more control over the size of pattern, and thus inks with high viscosities are preferred. In contrast to the molecular ink, multiplex deposition is possible by using a carrier liquid. For instance, with a viscous buffer, multiple proteins can be simultaneously deposited. Figure 2 shows the typical deposition mechanism of a liquid ink. Let us discuss now some advantages of the liquid inks are that the resolution is of the order of 1 to 10 microns. Then the multiplex depositions are possible using liquid inks as the deposition material. Then there is lesser dependency over ink or substrate in this method. Also, highly viscous materials can be directly deposited using this method. Typical examples include patterning of proteins, peptides, and DNA. In addition to these, hydrogels, conductive ink, lipids, liquid phase silanes, etc. can also be patterned. We will now discuss some applications of the dip pen nanolithography. For differentiating between good and bad DPN applications, understanding the capabilities and limitations of this technique is important. Direct write processes, example contact printing, can be used for patterning multiple biomaterials. However, its resolution is poor and it fails to form patterns at subcellular resolutions. Several high-resolution lithographic techniques are available which can be used to create features with submicron resolutions. But they necessitate expensive high-end equipments not developed for biomolecule depositions and cell culture. Another technique called microcontact printing can be used to create biomolecule patterns under ambient conditions. However, multiple patterns cannot be developed with this. DPN technique has various industrial applications. The potential applications are biosensor functionalization, that is, directly placing several trapping sites on a single biosensor. Figure 3 shows the cantilever-based biomolecule sensor, which is functionalized with 4 different proteins. Another important application of DPN is the nanosensors. This technique can be used to fabricate small and high-value sensors to identify multiple targets. Then, the nano-sized protein chips is another important application of DPN. Here, highly dense protein arrays having enhanced sensitivity can be prepared using this technique. Besides industrial applications, the DPN technique also has various emerging applications. Firstly, important one is the cell engineering. DPN can be used to manipulate cells with submicron resolutions for research purposes. This has many potential uses such as stem cell differentiation, delivering drugs to specific cells, cell sorting, cell adhesion, etc. Then rapid prototyping is another important application. It has applications in plasmonics, metamaterials, cell and tissue screening. Figure 4 shows the SEM micrograph showing gold metastructure arrays fabricated via DPN. We will next study the properties of dip pen nanolithography technique. It is a direct write process which can be employed for both top-down and bottom-up lithography applications. When used for top-down lithography, tip is employed to put etch resist on the surface. This can be followed by traditional etching. In case of bottom-up, the tip directly deposits the compound on the surface. Figure 5 shows the gold on silicon metastructure which is produced via top-down DPN. We will next study the advantages of DPN. DPN has the following unique advantages. First is the direct placement. This technique directly prints the material over an existing micro or nanostructure. Secondly, it offers the advantage of direct write. Patterns and features can be directly created without any mask. The resolutions achieved vary between 50 nanometers to up to 10 microns. Then biocompatibility is another important advantage of DPN. Since the technique can achieve sub-micron to nanometer resolutions at ambient conditions, it can be effectively used in biological applications as well. Scalability offers another advantage of DPN. It is a force-independent technique which can be used for parallel deposition as well. Let us now discuss about thermal dip pen lithography. It is a heated tip version of the standard DPN technique. This technique can be used to write semiconductor, magnetic, metallic, or optically active nanoscale particles onto a substrate. A suspension of the particles to be deposited is prepaid with PMMA or any other polymer matrix. This suspension is heated till the nanoparticles begins to flow. The probe tip works like a nanopin which creates patterns of nanoparticles in a programmed manner. The resolution achieved depends upon the dimensions of the nanoparticles and it can vary between 78 to 400 nanometers. PMMA can be removed by oxygen plasma etching. Now, the merits of thermal DPN include it does not require any mask. Also, it is highly advantageous as very low resolutions can be achieved using this technique. In addition, using the thermal DPN, a variety of nanoparticles can be written without any special solution preparation technique. Despite various advantages, it also offers certain drawbacks. Its drawbacks are that the nanoparticles must be smaller than the radius of gyration of the polymer. That is, for PMMA, the radius is about 6 nanometers. As the size of nanoparticles increases, the viscosity also increases, which slows down the process. For example, pure polymer can be deposited at 200 micrometer per second, whereas the addition of nanoparticle decreases it to 2 micron per second. However, thermal DPN is much faster than the standard DPN. Now, we will discuss the common misconceptions that one bear in mind. The first one is about the patterning speed. This is the most talked feature of this technique. It is usually compared with soft lithographic techniques such as micro contact printing, benchtop, microscale, and nanoscale patterning, etc. Out of these, micro contact printing is presently used standard in low cost printing. DPN is most often compared with micro contact printing, which is used to pattern one material over a large area in a single stamping step, which is analogous to photolithography patterning large areas with single exposure. In comparison to these techniques, DPN is relatively slow. Also, dip pen nanolithography does not use mask and thus it can produce several patterns on a single substrate of different sizes, shape, and resolution. Micro-contact printing cannot be applied to this scenario as it requires creating separate master stamp for all creating separate master stamp for all the features, which would be both time consuming as well as expensive. Furthermore, micro contact printing cannot achieve the resolutions on the order of nanometers. This misconception can be removed by understanding the application areas and methods of photolithography and electron beam lithography. Since in photolithography application areas, E-beam will obviously be slow, the same thing happens between DPN and microcontact printing. Another misconception regarding DPN is that it is related to atomic force microscopy. Since DPN has direct roots to the atomic force microscopy, it is only natural for people to think that all commercial AFMs can be used for DPN. Most surprisingly, DPN does not need AFM, and it is not necessary for an AFM to have DPN functionalities. The difference between both these can be best understood by considering the analogy to SEM and E-beam lithography. E-beam lithography has directly evolved from scanning electron microscopy, and both employ focused E-beam. However, both these techniques are not interchangeable at one another's application area. Figure 6 shows the microcontact printed strepta winding having a thickness of 4 nanometer. A very significant characteristic of DPN is that it is force independent. Virtually all ink and substrate combinations can be used to draw a feature regardless of the hardness of the tip against substrate and vice versa. While using robust silicon nitride tips, the feedback system, laser, quad photodiodes, AFM, etc. all can be avoided. So students, let us summarize what we have learned in this module. In this module, dip pen nanolithography technique was discussed. Also, the various materials which are used for the deposition were studied and the advantages were discussed in this module. Furthermore, applications of dip pen nanolithography were discussed along with its properties and advantages. In addition, finally, thermal dip pen lithography was also studied. Thank you students for your attention.